Hello, hello. Hi everyone. Am I audible to everyone? Or is anyone there watching this live stream? Because it was scheduled quite late, so you might not be expecting that the PCD would happen right now. But is anyone there regardless of the fact? And am I audible? So it looks like I'm audible. So I guess I will start and you guys will start joining in. So, hi everyone. Today we will discuss the today's Leetcode contest, which was the weekly contest, and we'll discuss all the four problems of it from A to D. Okay, but before we start, I'll tell you about our courses here at TLE Eliminators. So, if you're someone who is stuck at just solving one or two problems for a contest, then these self-paced courses are exactly what you need. So, we have divided these courses into four levels. So, you can start from wherever you are: beginner, pre-intermediate, intermediate, or advanced. Um, you will learn the most relevant CV concepts through video lectures by experienced educators, followed by carefully curated practice problems, combined with guided hints and detailed video solutions that help you understand the why and not just the how. You will, we believe in helping you build real intuition. And if you need more help, then you will get instant doubt support from our high rated mentors, so you are never left stuck. And beyond just learning, you will enjoy gamified progress tracking, leaderboards, PCDs, and internal contests to keep you consistent. Pick the level that fits your goals and start learning today. And if you're not sure that which level you should choose out of these four, then you can watch this video to understand that what is the best for you. And if you're still not sure, then you can watch the level specific video which details the prerequisites, outcome, difficulty, and topics taught in that course in that level, right? So, without a further ado, let's start the PC now. So this was the PC, like this was the contest of today, and let's go ahead and solve the first problem, which is called count monobit integers. So I said that if you are someone who can only solve one or two ground score counters, then you should like consider these courses because then it will increase to three or four as well. I did. I solved um, five, I guess. Yeah. Anyways, so let's start with the PCD. You are given an integer n. An integer is called monobit if all the bits in its binary representation are the same. Return the count of the monobit integers in the range 0 to n. Okay, so it is a pretty simple problem that they are saying that for an integer n, okay, if I write it in binary, let's say 1011, so this is 11 in binary, like the number 11 is this in binary. So they are saying that this number n is called monobit if all the bits in its binary are same, okay, without leading zeros. Like if we don't consider leading zeros, then all the digits should be same. So like in this case, this n is not monobit because it has both 0 and ones, right? So for monobit, it has to be same. Like all the digits have to be same. So either they should be all zeros, but of course we cannot have like this is not a number, right? Because these are four leading zeros. So like only possible case is zero, right? In binary. So this is a monobit number, okay? N equal to zero in binary, which is also zero in decimal form. So zero in base 10 as well. So this is one monobit number. And the another case, like either all zeros or all ones, right? So all ones means either 1 or 1 1 or 1 1 1 or 1 1 1 1 and so on, right? So like these numbers, they are the monobit numbers, right? And like you can notice that basically it's just a power of 2 minus 1, right? Like this is 1, this is 3, this is 7, and this is 15. So like you can see that this is 2 minus 1, this is 4 minus 1, this is 8 minus 1, this is 16 minus 1. So they are all powers of 2 minus 1, right? Actually, it is not useful. Like this fact is not useful in this problem, but I'm just telling you as a fun fact or something. Like if you add 1 to this number, then you get a power of 2, right? Because you get 1 0 0 0 0. So a number which is like 1 followed by a couple of zeros is basically power of 2, right? Because if the xth bit is 1, then this is 2 to the power x, right? So yeah, these numbers are powers of 2, and we have been given an integer n, and we have to like count that how many numbers in this range 0 to n inclusive 0 to n inclusive, how many numbers are monobit, right? So here n is given to be like up till 1000 only. So we can even loop for O of n. Like we can run a loop from 0 to n and check if this number is monobit or not. Like I from 0 to n and check if I is monobit or not. So we can do that pretty easily. Like let's say I want to do that. I'll explain how to do that. Like let's say I am iterating I from 0 to n. So how do I check if this I is of the form 1 1 1 1 1 1 or not? Like a couple of ones. So how do I check if this I is of the form 1 1 1 1 1? So for that, actually, there's a very nice trick. Like what you can do is, let's say my number is 1 1 1 1 1. Okay. So what you want to do is you want to check if it is a power of 2 minus 1 or not. So what you can do is you can add 1 to it. Okay. So what you'll get is 1 0 0 0 0 0, right? And so this is x, I mean this is I, and this is I plus 1, right? And if you notice, the bitwise and, like if you take the bitwise and of I and I plus 1, right? If you take the bitwise and of this and this, then all of them have 0. Like this is 0 0 0 bitwise and, right? So this turns out to be 0. Okay. And actually, if it turns out to be 0, then you will know that this I is the form 1 1 1 1 1. Okay. Like this works, that you can simply check the value of I bitwise and with I plus 1. And if it is 0, then this I is a power of 2 minus 1, right? So you can just iterate from 0 to n and check if I plus 1 is equal to 0 or not, right? So this is like an O of n solution, but you don't need to do that O of n, because even O of 1 is possible. Like how O of 1 is possible, what we can do is we can observe a pattern, right? Like the pattern is that, okay, first 0 is always there. Like the monobit number 0 is always there in the range 0 comma n, right? Then we have 1, then we have 1 1, then we have 1 1 1, then we have 1 1 1 1, and so on, right? So basically, you can say that whatever your n is, okay, like let's say n is of 4 bits, all right? Like let's say n is 1 0 1 0, right? So since n is of 4 bits, so all the numbers till 3 bits will come. Like this is of 4 bits, right? So this 4-bit number will not come 1 1 1 1, because it is greater. It is greater than 1 0 1 0. So we will only take these three and 0, right? That's the point. So basically, you can just count the number of bits in this number. Okay. And actually, one more thing is there. Let's say the number is 1111, right? So in this case, there are 4 bits, but you will still take this one because it is less than equal to n, right? This number is still less than equal to n. So you will take this number, right? So actually, what you can do is instead of checking less than equal to n, like you are counting the range 0 comma n, right? Inclusive. Instead of that, you can count 0 comma n plus 1 exclusive. That is, you can count this range. That is, you can count the number of numbers x such that x is less than n plus 1 instead of counting x less than equal to n, right? So you can compare with n plus 1. So if n is this, then n plus 1 is this, right? So it is 5 bits. And you want the numbers less than that, so they have to be less than equal to 4 bits. So this one, this one, this one, or this one, right? So basically, you can just see n plus 1 value. You can see the value of n plus 1, and you can count the number of bits, right? And the answer is just number of bits. Why? Because let's say number of bits is 5 in this case, right? So 4 numbers you have these two, 1 bit, 2 bit, 3 bits, and 4 bits. You have these 4 numbers and also 0. So basically, the answer is number of bits in n plus 1, right? Like if the input is n, then the answer is number of bits in n plus 1. All right. And to calculate this, you can use the built-in function, which is CLZ, count leading zeros. So what this function does is it will return the number of leading zeros. Okay. Number of leading zeros in n, right? So you can easily count the number of leading zeros. Let's say if n is an int, right? So it is 32 bits. So let's say I have 5. If n is 5, then basically 5 is what? 0, 0, 0, 0. Like we have 29 zeros and then 101, right? So if I calculate the CLZ of 5, then it will give me 29, right? And to then find out the like number of bits, I can subtract it from 32. So 32 minus CLZ of 5. Okay. So some of you might think that this problem is very basic, so why am I taking so much time? But it might not be basics for everyone. And some of you might not know the CLZ, and you might not know that n and n plus, like I and I plus 1, you can do this trick. So I'm just trying to educate some people with the help of this problem. Even though it is not required in solving, even though not all of this is required to solve this problem, because you can simply do it in O of n, and like you can do it any way you want. But this is the most efficient way because this CL is just O of 1 function. Okay, like it is a CPU instruction, so it is very fast. It is O of 1. It is not O of log n. Okay, so yeah, you can simply count the number of bits in n plus 1. Okay, so I have written, that's what I've written here. Basically n plus, like this is 1 plus CLZ of built-in CLZ of 1. So built-in CLZ of 1 is just like if 1 is an integer, like an int, 32-bit int, then its binary is 0000 and last number is 1. So we have 31 zeros here and a 1. So this will give me 31. And so 1 plus 31, which is 32. 32 minus CLZ of n plus 1. That's why I've written here 32 minus CLZ of 5. If I want the number of bits in 5. Okay. And why I did like this, like why didn't I just write 32? It's because if this one was long, let's say 64 bits, like let's say if your CPU has 64-bit integers, then um, then also it would work because this would return 63 and then 64 minus say that of this, so that would work. But if I wrote 32 here, then it would not work, right? So yeah, this was the problem one. Similar pattern, like I'm not aware of the like any standard patterns. Um, like I actually do CP, not DSA. So like I'm not aware of any standard patterns which are there. But I think if you listen to the explanation, like if you carefully understand the explanation, then you will understand that, oh, this is like I have done this previously somewhere. Okay. Anyways, so that's why you should participate in all the contests for practice at least. Okay, let's move on to second one then. Final element after subarray deletions. Okay, yeah, this problem was also like a pretty nice problem. So you are given an integer array nums. Two players, Alice and Bob, play a game in turns, with Alice playing first. In each turn, the current player chooses any subarray, nums L to R, such that R minus L plus 1 is less than M. So the length of subarray is less than M, where M is the current length of the array. This subarray is removed and the remaining elements are concatenated to form the new array. The game continues until only one element remains. Alice wants to maximize the final element while Bob wants to minimize it. Assuming both play optimally, find the final element. Okay, so this is a game problem, right? Like you have an array, right? Let's say you have an array 5, 2, 3, 1, 2. Okay, or this is a okay. Let's say this is the array, and what each person can do is in one move they can select a sub array of the array and delete it. So this would become 5, 1, 2, right after this move. So Alice goes first, and Alice can delete a number. Then it's Bob's turn. So Bob can also delete some sub array. Then it is Alice's turn. So this will happen until the length is 1. The array length is 1. So what will happen is the final number. Let's say if Alice deleted this two and Bob deleted these two, then final number is 5, right? So 5 is the final value, and Alice wants to maximize it. Alice wants that the final value is maximum, and Bob wants that final value is minimum. So if both play optimally, then what is the actual answer? Final answer, right? So, like basically in these type of problems, you should actually think of the tree, the game tree that will form, right? Like what is the game tree exactly? You ask. So let's say I have 5, 1, 3. Like an array is there, which is 5, 1, 3. So right now it is Alice's turn, right? So she has like she right now has how many? She has 5 options, right? Like either she can delete this 5 or she can delete this 1. Like, okay, either delete this 5 and make it 1 comma 3, or delete this 1, so make it 5 comma 3, or make it 5 comma 1, right? So these two options, or she can make it like 5 comma 1, or sorry, just 5, delete 1 and 3, or she can make it just 3, like delete these two, this subarray, right? So she has these 5 options. And what Alice, so okay, let's say Alice chooses this option, okay, and now it is Bob's turn. So Bob has 2 options, either to delete this 1 subarray or delete this 3 subarray, right? So either make it 3 or make it 1, right? Then here also Bob has 2 options, either make it 3 or make it 5, right? Then here also make it 1 or make it 5. And for these cases, the game is already over, right? Because there is only one element left. So um, the game is over already. Like Bob won't do anything. This is the final answer, right? For these cases. So now I ask you that, let's say if Bob gets 1 comma 3 and he has 2 options, either this one or this one. Like either he can make the final answer as 3 or he can make it as 1. So which one he will choose? He will choose 1, right? So if Alice goes here, then the final number would turn out to be 1. That's what this means. Like if Alice chooses this move, then the final answer would be 1. Then if Alice chooses this move, then it's Bob's turn here. So what will Bob do? Bob has 2 options, either 3 or 5. So Bob will choose 3, obviously. So if Alice moves this one, then the answer would turn out to be 3. Then here Bob will choose 1. So the answer for this state is 1. Then for this state, the answer is 5, of course, because uh, only a single number is left. And for this state, the answer is 3. So basically, we have Alice has 5 options, right? Like Alice had 5 options to go to either one of these states, and we have found out that what is the answer for each state. Like if Alice goes here, then the answer would come out to be 1. If Alice goes here, it would be 3. If she goes here, it would be 1. If she goes here, it would be 5. If she goes here, it would be 3. And since Alice wants to maximize it, right? Alice wants to maximize the answer, so she would go to the maximum state. Like she would go to the 5, right? So the answer is 5. Like the answer for this state, the starting state is 5, right? So this is what the tree is. Like it is not like it is not very useful in this problem, because of course you cannot check all the possibilities, right? That would just give TLE. But this is how a game works. That there are many possible moves, and for the like final states, like for each move, you will go to a state, right? And there would be some answer to that state as well. And Alice would choose the maximum possible value, and Bob would choose the minimum possible value. So this is what that game tree looks like. But now, why am I telling you this? I am telling you this because um, if you start with an array, right? Like you can start. Basically, Alice has the option to start with an array: 2, 3, 4, 5, 1. Let's say, right? So what will Alice do is Alice will basically delete one subarray, right? And this game will go on until there's only a single element left. So actually, if you can see, Alice can delete this entire subarray from 2 to 5, right? And the answer would be 2, right? So Alice can always make 2 as the answer. Also, she can delete this subarray, so she can always make 1 as the answer, right? So basically, there are many options for Alice. In fact, there are like 9 options to delete. Okay, not 9 actually. Wait. Yeah, sorry. 9 options. 9 options to delete, or not 9. 14 options. 14 options to delete, and but one of them, like she definitely has the option to make the answer 2, and also she definitely has the answer option to make the answer 1. But also there are other options. Like there are total 14 options. So we don't know the answers to these ones yet. Okay. But she definitely has the option to make 2 or 1, right? So definitely my final answer is greater than equal to 2, because Alice will choose the maximum one, right? So if there are some values in here which are more than 2, then Alice will choose that. But if all of them are less than 2, then she will just choose this 2, right? So definitely answer is at least 2. Okay, we know this right now. All right. But now um, we have to look at these cases as well, right? Like where Alice deletes the let's say this subarray or this subarray or so on. Okay. So if Alice does that, like let's say this is the case where Alice deletes this entire subarray, right? And this is the case where Alice deletes this entire subarray. So let's say that Alice does not do that. Okay, like this one or this one, Alice doesn't do that. Alice deletes some other random subarray, right? Like this, or maybe like this. So Alice deletes something else. Okay. So what will happen is in the final array, like my point is that let's say Alice deletes this subarray. Okay, 2, 3, 4. Or let's not do that. Um, okay, yeah, let's say Alice deletes 2 and 3. Okay, so Alice deletes 2 and 3. So she reaches 4, 5, 1. So now what will Bob do? Now actually, what Bob can just do is delete both of these, and the answer to this is 1. Like he can make the answer as 1 to this, right? So actually, the answer may or may not be 1 to this. Like actually, it is 1. In this case, it is 1. Like in 451, the minimum value is 1, and Bob wants to minimize it. So he can simply delete these two. Like what can he do better, right? But actually, my point is that in these cases, Bob will always be able to make the answer less than 2, less than equal to 2. See, um, whatever you delete, whatever number like or whatever subarray you delete, you will end up with an array here, right? Which has at least 2 elements, right? Like if Alice deletes a length 4 subarray, then it has to be either this one or this one. So we have already done those two cases, right? And she can get an answer of 2 from here. Now we want to only check if Alice can get a better answer from here. Like, can Alice do better if she chooses these cases? That is, we want the answer to be greater than 2, right? Like here, if we get something which is greater than 2, then we will choose that. Otherwise, the answer is 2, right? But my point is that whatever she deletes, either the final array will end in 1. Okay, like if she does not delete this one, the final array will either end in 1. Or let's say if she deletes this one, then or the final array will start with 2. Okay, that's my point. That if Alice deletes anything from this, then either the array will end with 1, the final array will end with 1, or the final array will start with 2 for all these cases, right? Like there are total 14 different options. 2 are these ones, and there are 12 more. So for all 12 of these cases, either the final array will end in 1 or it will start with 2. Because you cannot delete both of these, right? You cannot delete both of these because you have to delete the sub array. So if you delete this one, and this one, you would have to delete the entire thing, which is not allowed, right? So the final array for these cases would either end with 1 or start with 2. And so Bob can always like just delete this subarray and make the answer 1. Or Bob can always like for this case, he can delete the entire this thing and make the answer 2. Right? Like Bob always has this option. My point is that Bob always has the option to make the answer 1 or 2, depending on what Alice does. So if Bob has a better choice, then he will take that. But in the worst case for Bob as well, the answer cannot be greater than 2. Like Bob wants to minimize it, right? So he always has the option of 2. Like he always has the option of 1 or 2. So he will choose that. Like either he will choose that or he will choose something even less than that. But my point is that for these branches, it cannot get better than 2. Okay. There is no way that the answer for any of these states is a 3. Because Bob would never choose 3 answer, right? If he has the option of 2 always, then he will choose the 2 only. Why would he choose the 3? Right? So that is my point. That the answer for all of these branches is definitely less than equal to 2. Okay. And we are getting 2 from here. So definitely the best that we can do is 2 only. Like if I give an example, let's take a small example. Okay. 2, 3, 4, 1. Okay. So for this, how many are the possibilities? There are 9 cases. So I will draw all of them. Okay. So either you delete this subarray, so you're left with 2. So the answer is 2. Or you delete the first three elements, so the answer is 1. Or you delete, let's say, a single 2, so 3, 4, 1. A single 3, so 2, 4, 1. A single 4, so 2, 3, 1. Or a single 1, so 2, 3, 4. Or you can do 2 and 3, you can delete, so 4 and 1 you will be left with. Or you can delete like 3 and 4, so 2 and 1 will be left. Or you can delete 4 and 1, so 2 and 3 would be left, right? So these two are the cases which Alice always has. That final answer is the first or last value. So Alice always has the option of making the answer 2 or 1. So of course she will choose 2 if she has to choose between these two. But she also has other options, these ones. And my point is that the answer for all of these other options is definitely less than equal to 2. Why is that? Because you can see that all of these arrays, either they end with 1 like this, or they start with 2 like these ones. So Bob can always, like in any case, Bob can make the answer better than 1 or 2. Like in this case he can make the answer 1, and in these two cases he can make the answer 2. So definitely Alice can never do better than 2 from these cases. And since she can do a 2 from this case, she will just do that. Okay. So I think this should be clear. Like if you can just let me know if it is clear. Bi-weekly contest discussion. Yeah, it will be there. Like I think it would be recorded um, for that purpose. Was the bi-weekly last week? Okay, there was. So do you want to understand this, guys? Yeah, it will be uploaded. Anirudh, the recording will be uploaded on TLE's YouTube channel. So everyone, please let me know if you understand that why Alice cannot do better than 2. Okay. Okay. Will the answer be simply dependent then on 2 end elements? Yes. It would be the maximum of those 2 end elements. Didn't understand. Okay. So do you understand that Alice can make the answer um, 2 or 1? Like if she wants, Alice always has the option to make the answer 2 or 1. I mean, Alice has the option to make the answer 2. She has the answer option to make the answer 1, right? Do you get that part? That Alice always has the option to make the answer 2 because she can delete this sub-array, right? So do you understand that? Hmm. So now, um, Alice always has the option to do that. But what if she wants to make it like 3 or 4? Because Alice wants to maximize it, right? Alice wants to make it maximum. So she will try that the final element which remains is better than 2. Like she always has the option of 2, but she will try to make it better than 2 as well. But how can she do that? Like if she deletes some subarray, if she deletes some subarray, let's say any subarray, let's say either this one or maybe this one. So every subarray which she deletes will either like it will either start with a 2, right? Like either these subarrays, this subarray, or this subarray, or this subarray, right? Like either the final array will start with 2 if I did not delete this 2 in the subarray, or it will end with 1. Okay, like either one of these elements will always be there, whatever Alice does, because I cannot delete both of these. Because for that, I would have to delete the entire array, and we cannot do that, right? So, do you understand that the final array, like after one move, the array will definitely contain either 2 or 1 at the endpoint, right? Do you understand that? Yes. So now, if that is the case, like whatever Alice does, either the array will start with a 2 or the array will end with a 1. So let's say this array starts with a 2, then it is Bob's turn, right? So Bob can always just delete this part, this suffix, and get the answer 2. So Bob always has the option to do this. Like Bob has multiple options, but one of the options is to just delete this entire subarray and get the answer as 2. So Bob will do that. Like Bob will either do this or he will do something even better for himself. That is even lower. But what we can say is that the answer for this state is definitely less than equal to 2. Sorry. Because Bob always has the option to make the answer 2. So either he will choose that or he will choose something even better. Right? So the answer is definitely less than equal to 2 for this case. And for this case, the answer is definitely less than equal to 1, in fact. Right? So if Alice chooses this, then it is a very bad decision because the answer can't be more than 1. And if Alice chooses this one, then in best case also the answer is less than equal to 2. So you cannot get a better answer than 2 in any of these cases. So you can simply choose this case to get the answer as 2 because that is the best you can do, right? So do you understand the, like you can think from the POV of Bob. Like whatever the array is, let's say it starts with a 2 and ends with a 1. This is the initial array. So whatever I do, let's say I am Alice and you are Bob. So whatever I do, let's say I delete this subarray. So you have an array which has 2 at starting and 1 at the end, right? So what you will do is you can delete the entire subarray and get the answer as 2. Or you can even delete this entire thing and get the answer as 1. So since you can get the answer as 2 or 1, definitely your answer is better than that, like less than equal to 1, right? So if I know that, then I won't choose this subarray. I'll simply take the answer 2. Okay, so All right. So I think everyone understood this. So let's look at the code. So code is nothing. Code is just return max of nums 0 and nums dot back. Okay. So code is अगर बॉब की टर्न फर्स्ट होती तो आंसर्स min of n elements. Um, I mean, yeah, because the same logic, like if it was Bob's turn first, then same logic, like 2, 3, 4, 1. If Alice wanted to maximize and Bob wanted to minimize, so whatever Bob does, either the array will um, start with a 2 or it will end with a 1. So Alice can always get 2 in this case and 1 in this case. So definitely the best possible answer is 2 or 1. And Bob can definitely get 1 if he deletes this, if he deletes these elements. So he will get the answer as 1. That is correct. So yeah, let's move on to the next one now. So C is like very like simply no logic is there for this C. It is a pretty simple problem. I don't know why they're asking these kind of problems in the contest, but okay. A ride sharing system manages ride requests from riders and availability from drivers. Riders request rides and drivers become available over time. The system should match riders and drivers in the order that they arrive. Implement in the class. So there's a constructor which we can use. Then void add rider int rider ID. So it adds a new rider with the given rider ID. Add driver ID. Adds a new driver with the driver ID. Match driver with rider. Matches the earliest available driver with the earliest waiting rider and removes both of them from the system. Returns an integer array of size 2 where result is driver ID, rider ID if a match is made. If there is no match available, then returns -1 -1. And void cancel rider cancels the ride request of the rider with the given rider ID if the rider exists and has not yet been matched. Okay. So this is a simple problem. Like what they are saying is that we have like some ride, like there are a few functions we have to implement. First function is add rider. Okay. So what add rider does is it will basically add the rider to the queue. Okay. And what add driver does is it will add a driver to the queue. And then if match function is called, right, then we have to match the earliest rider with the earliest driver. Okay. And remove them from the queue. Right. So for example, let's just look at a test case to understand the problem a bit better. So yeah, ride sharing system dot rr3. Like this is the first command. First is the initial like constructor, so it doesn't do anything. Then add rider 3. First command is to add the rider 3. So let's say we have two things, riders and drivers. Okay. So what riders? So okay, add rider 3. So add rider 3 means we have to add the rider 3. So 3 will get added. Then add driver 2. So add driver 2. Let's add this driver 2. Then uh, add rider 1. So add rider 1. Then match driver with rider. So what it will do is it will match these two, 3 and 2. So it will return 2 comma 3, right? Driver ID and rider ID. Okay, and then it will remove these two from the queue. Okay. Then add driver 5, add driver 5, then cancel rider 3. So since 3 is not there, like only 1 is there, so nothing would happen, right? Then match driver's rider. So it will match 1 with 5. So 1 and 5, like the output would be 5 comma 1, driver comma rider. And then again match is called, but there are no drivers and there are no riders. So if there wasn't either one of them, the answer would be -1 -1. Like match is not possible. So both have to be there for a match to be possible, right? So we have to implement this functionality. And like you can think about using a queue, right? Like to implement this, you can simply keep two queues, right? One queue would be for the riders and one queue would be for the drivers, right? And you can simply keep inserting in the queue. Like here, as you can see that three came, so we inserted 3 here. Then 2 came in the driver. Then let's say more elements would have come. So let's say rider 4, rider 5 is also there. And then we have to match. Let's say match is called. So we'll match the first one with the first one, right? So basically we have to pop the front of the queue. So it's basically first in first out, right? That's why we're using a queue, right? But now the problem lies that what if there's a cancel? What if there's a cancel request, right? Cancel rider. That is, we would be given a rider ID, and we would have to like cancel his order. So like let's say we have 3 4 5 in the queue 1 and 2 in the second queue. So and you have to cancel 3. So you have to, or let's say we have to cancel the 4, right? So we have to remove this 4 from the queue somehow. But that is not allowed, right? Like in a queue, we cannot remove elements from the middle or the end also, right? So we cannot really do that. So how do we do that? Like how do we make a queue which supports deletion of elements from the middle as well? How can we do that? So do you have any ideas? So it is not very hard to think of. So can you tell me how to do it? Like how do you implement a queue? Like actually you can use something else. You don't have to use a queue, right? You can use something else. But basically the operations that you have to use is that you have to insert, you have to delete, and you have to find the smallest the first element, right? Okay, map. Linked list. Actually in linked list you would have to find the element, right? Like if you have a linked list 3 4 and 5, you don't know that where is 4, right? So you would have to iterate over the entire linked list to find it, and then you would delete it, right? So that is not ideal. But what you can do is you can use a map or a set, right? I used queue. So how did you like delete? Okay, rider avail and driver avail. Okay, that is also fine. That's actually a nice solution. Store the IDs in set. Yeah, you traversed and copied. So like your operation was not O of one. Like your worst case complexity is O of n, right, Jignesh? Yeah. So I don't know why it passed. Like okay, Leetcode maybe it is allowing O of n, but we can do it better. Like we can do it in O of one as well. or actually not O of 1, O of log n we can do. Okay. Um, or can we do O of 1 as well? Because the IDs are till 1000 only, so actually we can do O of 1 as well. So let's try to do that. Like I have solved an O of log n, so I'll improve that and we'll make it O of 1 together. Okay. So yeah, that this idea is very nice. That you took two queues, one for the rider and one for the driver, and maintain two maps, rider available and driver available. So what this guy did, like let's say we have two queues, right? One rider, 345, and one we have driver. Okay, let's say we have two. So now if I want to delete a four, right? I want to delete this four rider. So what I will do is instead of deleting it directly from the queue, like I can't do that, right? In queue we cannot delete from the middle of the queue, right? So what we'll do is we will store a boolean array, okay, which is called rider avail. Rider avail will store this boolean array, which is basically um, like it will store 0 or 1, like either true or false. So it will be true if that rider is in the queue, like if it should be there in the queue. Okay, so like initially, um, let's say this is the boolean array. Okay, so initially 0 1 2 are false and 3 4 5 is true. Okay, so when let's say you want to delete this 4. Okay, so what you will do is you can, instead of deleting it from the queue, you can simply set this to false. Okay, and have this said that the same rider does not appear. Okay, each rider ID is unique, right? This is also important. So yeah, you can just simply set this to false. So how that helps is, like let's say there are more drivers, 6 and 7. Okay, so now when I want to match, okay, so what I'll do is I will look at the front of the queue, so 2 and 3. So I'll match 2 and 3, but I'll also check that is these three actually there? Like, does this three actually have to be there? So yes, because there's a true on the three, I know that this three has to be there. Okay, so I'll just match 2 and 3. So I'll return 2 comma 3, and I will delete them from this array, right? Or the queue, I mean. Then let's say again match is called, so I have to match 4 comma 6. But since there's a false on this 4, that means I have already deleted the 4, right? So actually this had to be deleted. So I will delete it, right? And then again I look at 5 comma 6, and since there's a true on the 5, I'll simply match them. Okay, and I'll return 6 comma 5, right? And actually you can, like when you are matching them, like let's say when you match 3 and 2 and you deleted them, you can set this 3 to false also. That's fine. But even if you don't, that's also fine, because this 3 will never come again in the future. Like they have said that all the rider IDs are unique, right? So this will never come again in the future. Okay, so you can do this, make a boolean array, and the constraint are till 1000 only. So that's why you can make this boolean array, right? So that's how you can do it in O of 1. Now actually you might be thinking that how it is O of 1, like why it is O of 1, because in the, like if you can see in the match operation, you are actually checking the first of the riders, right? Like let's say you have a long queue. Okay, one two, like the riders queue is like 4 5 2 3 1 6. Okay, and let's say my driver's queue has only a single element. My driver's has 7. Okay, so and let's say that 1 2 3 4 5 6, 1 2 3 4 5 6. This is my boolean array. This is my boolean array, and like let's say we have false on 2 3 4 and 5. Okay, and true on 1 and 6. So basically, even though these elements are in this queue right now, but there is false written on them. So basically, they have been cancelled, right? So now, if you see, you will first check 4, and since there is false on the 4, you will not match that. Then you will check 5, and since there is false on the 5, you will not check that. Then you will see 2, since there is false, you will not match that, and then you will check 3, since there is false, you will not check that, and then you will look at 1 bit true है, so you will match 7 and 1, and you will return 7 comma 1, right? But so you can see, in this case, this match function actually it is taking off and time, right? Because in the worst case it might happen that all of these numbers, they are in the queue, but all of them are false, and only the last number is true. So we have to like spend off and time to match the rider with the drivers, right? So is this really so? Like, do you understand why one match operation might take off? And like, do you understand till here? All right. Okay. Leetcode directly add coder. So add coder will be uploaded by evening, and I think Leetcode also would be the same. But okay, so do you understand my solution, guys? First of all, do you understand what I am doing? Like, I'm just keeping a boolean array or a hash map basically, which stores that is the rider still available, or if he has cancelled. So if he has cancelled, then we will change the flag from true to false, right? And then when we want to match, so before we match, we will check if the rider are already cancelled or not. And if he has cancelled, then we will not match that. Instead, we will delete it from the queue and we'll check the next element, right? So do you understand the solution first of all? Okay, so Sachin, Komal, these like they understand how it works, right? And do you also understand why it is O of n? Like why one operation, one match operation, in the worst case, it might take O of n time, right? Do you also understand that? Okay, so but actually, what? So okay, like now you might think that since the cost of one operation, like the match operation, the worst case cost of that is O of n, right? So therefore, if there are q operations, then you might think that the complexity would be O of n into q, right? That is, if there are approximately n operations, then complexity is O of n square, right? So you might think this, right? So do you think this, or does someone not think this? Like, is there someone who disagrees with this? Anyone? Did you solve all of them by contest? No, actually, I woke up at 9:45 and I solved all of them. I think by 10:15 or 10:30 or something. But yeah. So anyone who disagrees, is there anyone who doesn't agree that it will take n into q time in the worst case. Okay, my question is that what is the time complexity of my solution? Okay, so what is the complexity of my solution? So you might think that okay, since this match operation, like when I'm doing the match operation, I'm checking the rider if it is false or true, right? And as you can see here, if there are many riders which are false, like this is false, this is false, 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 so my match operation can take off n time, where n is the number of riders in the queue, right? In the worst case, my match operation, it can take off n time, right? So for one operation, like for one match operation, if you have O of n time in the worst case, then if I do total of q operations, then my worst case time is O of n into q, because for one operation it is n, so for q operations it is n into q. So basically, if there are approximately n operations, like if q is equal to n, then it is O of n square, right? So do you agree with this, or does anyone not agree to it? No means you don't agree. So why do you not agree? It won't be n square. Acha, you agree. Okay. So Sachin says it will not be n square. So what it would be, Sachin? Like Sachin, can you tell me what it would be? Not agree. Okay. Jignesh doesn't agree because it won't get back the deleted elements. Vanshi, Vanshit Gaur agrees. Vamshi agrees. So okay, Jignesh doesn't agree because if q equal to n, we'll get O of 1 for each query. Okay, so actually the correct answer is that you should not agree. Okay, like this O of n into q, it is wrong. Like this statement is wrong. Like actually, um, my algorithm in total, it will only take O of n time, like or like order of q time. My algorithm will only take order of q time in total. Okay, not n into q. So this might be surprising for you guys, but why it is so? So you might have heard of amortized analysis. Amortized analysis. Okay. So basically, what I am saying is that okay, in the worst case, in the worst case for one operation, my match operation, I might be taking O of n when there are many people in the queue. Like if there are n people in the queue, and um, if I have to delete all of them, right? Then it will take O of n, right? But that does not mean that on every operation I will take O of n. Like actually, if you try to make a test case which takes O of n time on every operation, then you will definitely fail, right? And actually, that is because, let's say, like basically intuitively, if you understand that, okay, I said that if you have this state, that if you have 4 5 2 3 1 6, and there is a false on 2 3 4 and 5. Then what does that mean? That means that I must have inserted this 4, inserted this 5 2 3, right? There must have been at least 4 operations which had inserted 4 5 2 and 3. Like there must have an operation insert 4, then insert 5, insert 2, and insert 3, right? And also, since they are false, that means there must have been more operations which are cancel 5, cancel 2, and cancel 3. So these 4 operations also must have also been done. So by now, at least 8 operations have been done, right? At least 8. And then on the ninth operation, if I try to match, actually not even 8, we have to insert 1 and 6 as well, right? These two as well we have to insert. So insert 1 and insert 6. So by now at least 10 operations have been done, right? And each of them have taken only O of 1 time, right? Because insertion and cancellation is O of 1, right? So by now these 10, at least these 10 have been done. And then we have one match operation, right? And that is taking me O of n time, like to delete these elements. But actually to get to this part, I had to do 10 operations. And then only on one operation, match, uh, I delete all of these numbers. So like if you see, for this total thing, I am only spending O of 1 time on all of these and O of n on this one. So like this cost gets divided amongst these, right? So like per query you can think of it as O of 1 only. Like see, um, like let's say I have these q queries. So these q minus 1 queries, except for the match one, these q minus 1 queries took O of 1 time, and only the one match query it took O of q time, let's say. So total, what is it? Like total is 1 into q minus 1 plus q into 1. So it is 2q only, right? So it is order of q only. Like why it happens? Because just to get to this state, you need so many operations. So you can actually divide the cost of your expensive operation into the smaller ones, right? And that is called amortized analysis. Like actually, what you can prove, like see, whenever you are matching, right? Whenever you do a match, um, you would be like you would have a rider's queue, right? You have a rider queue. So in match operation, you will always delete elements from this queue, right? And in your insert rider, you will always insert elements into this queue, right? And also each element is inserted only once in the insert operation, and removed also only once in the match operation. So for each element, we do only two operations. We do only two operations. So actually, my complexity is only 2 into number of elements, and number of elements also can only be up to q only, right? Because uh, on each query, at most one new element might be added, right? So therefore, my complexity is actually O of q. The total complexity is O of q. Okay, that is per query. It is O of q upon q, which is O of 1. All right. So that is called amortized analysis. Okay. Yes, that is what I have explained right here, right now. And you don't even need a set. You can simply use like a boolean array, so that is faster, because set is O of login and array is O of 1. Okay, so yeah, do you guys understand this? That you can kind of divide the cost of the heavy operation into these lighter ones, because we know that there are enough light operations to divide the cost. Okay, all right, so let's write the code now. Like this code that I have written is actually log n per query, because I did not think of this approach. So let's code it right now very quickly. So let's say we have an array, bool rider present, avail rider, okay, which is a 1001 length, okay, and let's say we have two queues, queue of int riders and drivers, okay. So in the constructor we don't need anything. Then add rider, so riders dot push rider id, then add driver may also, yeah, do avail rider of rider id as true, then add driver may drivers dot push driver id, okay, then match driver with rider. So while riders dot size, just a minute, just a minute guys. Just a minute, sorry for the interruption, 1 minute. Yeah, so for matching we'll do while riders dot size and drivers dot size. First of all we'll check, so int rider is equal to riders dot front, okay. So if avail rider of rider, so if this rider is available, then we will return the answer. Like let's make a vector of int answer, and initially minus one, okay. So if I will write a rider, then we will set ans of 1 equals to rider and ans of 0 equals to drivers dot front and drivers dot pop. And yeah, here we can do riders dot pop. Okay. And otherwise, this means that the rider must have been deleted or cancelled, right? So we will simply not do anything. Okay. And this while loop will keep going on until either we, okay, and yeah, we'll break also. So if this is true, we'll break. So until either we break or the size of one of them becomes zero. So if we get into this is if statement, that means the answer, we found the answer and we have set it to the index. Otherwise, it is minus one minus one. So we'll just return it at the end. So return ans. Okay. And for the cancel rider, we can simply avail rider of rider ID equals to false. Okay. So let's try to run this. We get comparison error. Okay. Uh, yeah. All right. So this was C problem. And before moving on to D, I will like, sorry for the interruption. I'll get back to you at 12:35. Okay. Hello. Yeah, sorry for the interruption. From where should I study DNC DP? So DNC is a very advanced topic. Like even I don't know. I think divided copy DP. But if you want to study, I think there's a article on Usako guide DNC DP. So maybe you can read this. This is platinum topic by the way. So bronze, silver, gold, and platinum. So if you want to study, you can study this, but it is a very advanced topic. All right. So let's move on to the next problem. This is the last one for today, which is called a very long name. A longest alternating subarray after removing at most one element. You are given an integer array nums. A subarray is alternating if one of the following holds. Nums L is less than nums L plus 1, which is greater than nums L plus 2, which is less than nums L plus 3, and so on. Or nums L is greater than nums L plus 1 or less than, which is less than L plus 2, and so on. In other words, if we compare adjacent elements in a subarray, then the comparisons alternate between strictly greater and strictly smaller. You can remove at most one element from nums, then you select an alternating subarray from nums. Return an integer denoting the maximum length of the alternate subarray that you can select. A subarray of length 1 is considered alternating. Okay. So, like what we have is that we need to basically, like we have been given an array. We have an array. Okay. Let's say A1, A2, A3 up till AN, right? And what we can do is we can choose to remove at most one element. Okay. Let's say we choose to remove this, and then we can select a subarray. Okay. And that subarray has to be alternating. That is less than, then greater than, less than, then greater than, then less than, then greater than, then less than, then greater than. Like this is how the graph of the subarray should look like. It should be alternating, right? Like basically, if I delete A3, so the subarray is A2, A4, A5, A6, and so on. So the subarray has to be alternating. That is, let's say A2 less than A4, less than A5, less than A6, or um, A2 greater than A4, less than A5, greater than A6, and so on. Like that's how the subarray has to be. So we can select any alternating subarray, any alternating subarray, and we have to basically select the longest one, find the longest one, or the length of the longest one. Like output the length of the longest one. Okay. So actually, before solving this, it will help if you have solved the maximum subarray sum problem. Maximum subarray sum, uh, which uses the cadence algorithm. Cadence algorithm. Like I don't know why this algorithm has a name, but it is simple DP. So if you know the DP solution of the maximum subarray sum, then I think it would be easier to understand this problem. Okay. So let's start with the samples. So samples have 2, 1, 3, 2. So this is a very bad sample because the entire array is already alternating. So 2 is greater than 1, which is less than 3 is greater than 2. So we can just select the entire subarray, and yeah. Then this second sample, 3, 2, 1, 2, 3, 2, 1. Um, okay. So what we have here is, what they are saying is we can remove this 2. Okay. If we remove this 2, then we would be left with 3 2 1 and then 3 2 1. So I guess they are saying that 2 1 3 2. This is the required subarray of length 4. So like this is the, like 4 is the maximum possible answer we can get. So that's why 4 is the answer and we output 4. Right. So this is the sample. And yeah, basically we can choose to remove or not remove an element, and we can remove any element. And finally, we have to select the longest subarray from the array, which is alternating, right? So have you guys done this problem without the deletion part, like longest alternate subarray? I think this problem is very similar to what we are about to solve. So if you already know the solution to this one, okay, this is not. Wait, this is something else. Okay, let's say like we just solve the same problem without deletions. Okay, like let's solve a similar problem to this, that we have to find out the maximum length of a subarray, which is alternating. Basically, maximum length of an alternating subarray. Okay, and we cannot do any deletions. All right. So then, in that case, what is the maximum length, and can you solve that? Let's think about it first, and then we'll solve this harder version. Okay. So do you have any idea how to solve that? Okay, yesterday's Leetcode was last. Oh, is that so? Let's see. Doesn't sound like it. I don't think this is the um, same problem. I think you are asking a doubt. Is that, like, I don't know about that. I haven't read that. You can watch the PCD for Leetcode bi-weekly, which will be uploaded. Um, Anyways, so my question is, guys, that for this problem that we have at hand, we can delete one element in this, and we have to like find that what is the answer, basically, that what is the maximum possible length of an alternating subarray. But can you guys solve this if we cannot delete an element? Like in the original array, we have to select an alternating subarray. So, and what is the maximum length of an alternating subarray? That is the question. Okay. So, can you solve that? So, anyone, any ideas to solve that easier version? Okay, solve this question by prefix suffix. Prefix suffix, I don't understand how that would work. This question by like by this, do you mean lead code problem or my problem? Okay, I guess you mean lead code problem, that if we delete the element I, then the answer to the prefix of I, like the answer to the elements before I plus the elements after I. But it's not necessary like that. Initially, okay, you might be correct somehow. Yeah, I think you are correct. You can do it as like you can do it in that way as well. But okay, initially you thought to apply all the possibilities like removing every index and then finding the max alternative survey for giving TLE. So okay, can you tell me how you found the max alternating survey? How did you do that? Sliding window. Sliding window. Like you mean two pointers, right? So actually, that might. Hmm. Like how do you know whether to? Okay, sliding window might work actually. Yeah, I understood. I got it. Right. I think you are like Anirudh. Did this get accepted on Leetcode? Okay, Nikhil said DP. Okay, yeah. So this is also fine. What Crazy Blaze has said, but yeah, actually, okay. Only take the case in subway recursion and skip the not take case. Okay. So I think you guys are very close. Like I guess you might know the answer. Like some of you are correct also. So let's say we have the array. Okay. So one of you suggested the method to iterate over the array. Okay. So 3 to 1, 3 to 1 to 3 to 1. This is the array. Okay. So let's say I want to find out the maximum length of an alternating sequence which ends at this index. Okay. Like basically, I want to find out the maximum length of an alternating sequence which ends here. Okay. So basically, of course, this is a correct sequence because 2 comma 1 is alternating, right? Okay. Then if we try this, so then it is not alternating because this sign is same as this sign, right? That's why you cannot take this subarray. That's why you can only take until here. Okay. So for this index, the maximum that we can go is still here only, right? Then similarly for this index 2, the maximum that I can go is only till this, like because of course this is the first index, I can only go till here, right? Then let's say for this 3, or let's say okay for this 2, till where can I go? So I can of course go till here because it is not equal, but also I can go here as well because this sign is opposite to this sign, so it is alternating. And can I go here? No, I cannot go here because it is the same sign, right? So like this, like basically I am trying to find out that for every index till where can I go? Okay, for every index till where can I go such that the subarray is alternating, right? So basically I want that my um, signs should be different. Like let's say in this array, if I find out the signs, let's say greater than, then greater than, then this is less than, I'll use a different color. It's a yellow. So this is greater than, less than. Then we have less than. Then we have again greater than, and then we have greater than. Right. So I want to choose a subarray such that the signs are alternating. So like I can choose this subarray because these two signs are alternating, or I can choose like this subarray because these are alternating, or I can choose any length 2 subarray as well, as long as they're not equal. Okay, let's say if 1 and 1 is there, so they are equal. So I cannot choose this subarray. Okay, but yeah, so what I can do is like I want to find out that for each index I, or let's say for each index R, for each index R, I want to find out the minimum value of L, minimum value of L, such that my L comma R subarray is alternating. Okay, so like let's say if I index this 0, 1, 2, 3, 4, 5, and 6. So for the answer for 0 would just be 0. Then for the 1 it would be 0 because we can take this subarray. Okay, then ending at 2. So since these two signs are same, so actually I cannot go till here, right? That's why the answer is only till 1. So the answer is 1. Now for the answer for 3. So since I can like this in this one and this one they're opposite. So I can go till 1 from here, right? Like basically from the index 3, since this one is opposite to this one, I can simply append this at the end of the list. Like I know the answer for the second one, right? Like I know that till where can I go from second one? Like how far left can I go? So whatever is the longest sequence, I can simply append 2 to the end of it because 2 is greater than 1. And I know that the last one was this 1 is less than 2, right? So I can simply append 2 to the end of it. So from 3 also, I would be able to go till the point where I'm able to go from 2. Are you understanding that since I know, or let's say I draw a better diagram. Let's say I have a long array, very long array I have. Okay, and I have, let's say, a 1 here and a 2 here and a 1 here. Okay, and I know that from this index till where can I go to the left. Let's say I can go here. That is the subarray from here to here. It is alternating. Okay, like this is the last index, like this one, and this entire subarray is alternating, and this is the maximum, right? Now let's say I want to find the answer for this one, that from here how far left can I go. So since this is like this sign is like this is opposite to this, right? So that means that I can actually just include this one also at the end of this sequence, and that subarray will also be alternating. So actually from here also I can get till the end. Okay, that's the point. So if my this sign is different from this sign, it is opposite, then actually I can, then actually my answer, like my answer for 3 is the same as the answer for 2. Like till where can I go? I can go till here, index 1. So the answer is index 1, right? So actually if you see, if the sign, if the sign is same, then my answer of I is equal to the answer of I minus 1. Okay, and if my sign is different, like let's say uh, sorry, if sign is different, then answer is same. If the sign is opposite, if my sign is opposite, then the answer for I is same as answer of I minus 1. And if sign is same, then the answer of I is just I minus 1. If they are unequal, and if they're equal, then it is I. So like if you see, um, 1, 2, 3, 2, 2, 3 and 4. Okay. So here the answer, I'll index this also, 0, 1, 2, 3, 4, 5, 6. So like the answer for 0 always 0, of course. Then the answer for 1 is like we can go till 0, right? So it is 1. The answer is 0. Then here these two signs, they are same, right? So actually we can only go till here. Okay, so the answer is 1. That is for I, the answer is I minus 1, right? Then this sign is alternating, so these two are different. So the answer for this one is same as answer for this one, which is 1. So we get the answer as 1. Then for this index, so okay, now for, these two are equal, right? So if they're equal, then the answer is just like you cannot even go till here, right? This is not a valid subarray, so you can only go till here. So the answer is 4. Okay. And now for this thing, since these two are equal, um, the answer to this is also 4, right? You can only go till here. And now what about this one? Since this 3 is less than 4 and 2 is less than 3, so they are same sign. And since it is not equal, like since 3 is not equal to 4, my answer would be 5. Like 6 minus 1, which is 5. Okay, so you understand how to do this. Like basically I'll write the cases for the answer of I. Okay, so if the sign between I minus 2 and I minus 1, if this sign is opposite to I minus 1 and I, then the answer for I is same as answer for I minus 1. Okay. Also, like if I minus 1 is equal to I, if A of I minus 1 is equal to A of I, then the answer is just I. Okay. If A of I minus 1 is equal to A of I, then the answer is I. Answer of I is equal to I. Then what we can do is, yeah, if it is opposite, then it is answer of I minus 1. And if it is same, if the sign is same, then the answer of I is equal to I minus 1, if they are not equal, right? So this is how you can find, basically this is how for a given array, for every index, you can find that till how much left can you go, right? And so let's say for I, you have answer of I, that is till how much left can you go. And so the length of subarray is what? I minus answer I minus answer plus 1, right? So you can simply take the maximum of this quantity for over all indices. Like you know, right, that ending at this index, what is the length of maximum subarray? Maximum length of subarray. So for every index you will check that ending at that index, what's the maximum length? And so you will get the maximum length of a subarray, right? But now this is the problem. Okay, now this was a solution for the problem where you did not have to delete one element. Like you cannot delete any element, right? So that this is the answer for that. So do you understand this part? That how I got the answer for um, when my answer, like when I cannot delete an element. So do you got the answer for that? Okay, very nice. So now, if I can delete now, if I can delete an element, I can delete an element. Then what changes? Like first of all, of course, I can choose not to delete an element, right? That's one thing. Like it is up to me, right? That I can also choose not to delete any element, right? So the answer that I get from this thing, like from this method, whatever answer I get, that answer is there, right? But the question is that can I do better? Okay. So let's say I delete some element, that is a1, a2, a3, a4, a5, and a6 and a7, right? So if I delete a4, let's say, if I delete a4, then that means that um, I am selecting a subarray, which is like this. Okay, like if I delete this a4, then that means I am selecting this subarray, like some subarray, which is alternating, right? Like a2 is, let's say, greater than a3, a3 is less than a5, a5 is greater than a6, and a6 is less than, okay, let's say we take till a6. So we select this subarray right here, right? Like from both sides, I would be choosing some element. Otherwise, why would I delete this a4? Like let's say if I delete the a4, let's say if I delete the a4 like this, and then I choose this subarray, then what is the point of choosing a4? Point of deleting a4, right? Because I could have just chosen this subarray without deleting a4, right? So if I am like if I am deleting a4, then definitely um, like if I am deleting a4, then definitely I am taking some elements from the left and some elements from the right. Okay, and like you saw how we learned how to find the answer for a3, right? Like we saw that if we start from here, then how much left can we go? That is our question, right? And so like we know how to answer that question, right? Like we know that how to answer that if we start from here, how much left can we go? We know this quantity, right? So similarly for this a5, if I find out that if I start from here, how much right can I go? Okay, and then I can add those two quantities. Like if this sign is compatible, like let's say if a3 is less than a5 and this a5 is less than a6, then like basically I can go till here. I mean, sorry, a5 is not less than a6 if a5 is greater than a6, and also a3 is greater than a2. I mean, sorry, a2 is greater than a3. Then in this case, we can take this entire a2, a3, and a5, a6, right? So basically, the answer, like the left answer for 3 plus the right answer for 5. Like this is a possible answer if the signs match. Like if this a3, basically a2, a3, a5, and a6, they have to be alternating, and in that case only we can get this answer. Like in general, if you see, if we have an array from a1, a2, and then we have some elements, let's say ai minus 1, ai, a of I plus 1, I plus 2, and so on. And let's say I delete this element ai. That means I am choosing some elements from here and some from here. So like I know that if I want, if I am starting from I plus I minus 1 and I want this to be alternating, then till where can I go? I know that, right? And if I start from I plus 1, and if I want my salary to be alternating, then till where can I go? So actually, if you delete this AI and you look at the entire thing, then this also may be alternating, provided that this new sign that came here also has to be consistent, right? Like let's say we have a of I minus 2, I minus 3, I minus 1, then AI, then I plus 1, and I plus 2, let's say. And let's say we delete this AI. So what will happen is that uh, this sign right here between I minus 2, I minus 1, then between I minus 1, I plus 1, this sign, and between I plus 1, I plus 2, this sign, these three must be alternating. Okay, they must be alternating. And if they are alternating, then we know that आगे तो alternating है ही. Like we know that till what index these are alternating, right? And what index these are alternating. But we just have to ensure that these three are also alternating, right? And then we can use the left answer for I minus 1 plus the right answer for I plus 1. And actually, this left I minus 1 plus right I plus 1 means this left and right means what? Actually, left and right means the number of elements. Like left of I plus I minus 1 means the number of elements that I can take. And right of I minus 1 also, I plus 1 also means the number of elements that I can take from the right. So total number of elements is left plus right. If I delete this I, right? So I can simply compute the left and right arrays for all the indices, and I can iterate from I equal to 1 to n minus 2. Like of course I won't delete the first element or last element, right? So I'll iterate from the elements I'll iterate over these elements, and then I will check that can I use left of I minus 1 and right of I plus 1. I can do that only if this sign between I minus 2, I minus 1, I minus 1, I plus 1, and I plus 1, I plus 2. These three signs should alternate, right? And only then I can use this answer left of I plus 1, left of I minus 1 plus right of I plus 1, right? So I'll iterate over this I from 1 to n minus 2, and I will take the maximum value, maximum answer. Okay. So this was the solution for this problem, and I'll code it in front of you. But before that, I'll um, take any doubts if you have. Yesterday's bi-weekly, it will be uploaded. So yeah, this was the solution for D. So do you guys like understand how this approach worked? That if I delete an index I, then I can take the prefix of I minus 1 and suffix of I plus 1. And even in like Cardan algorithm, like in the problem where you can delete an element and then you have to find the maximum subarray sum. So even in that problem, you can do it like this. If you have solved the problem, then this one must also be very easy for you. Okay. DP on subarrays, like what do you mean? Like do you mean that I can use DP also? I mean, yeah, I have used deep. Like, how can I learn it? Okay, so DPM subarrays is not a like. I don't think it is a actual topic. Or okay, if you mean the n cube DP types, then again, Yusafa guide is a very useful Yusafa guide DP. So there is this subarray DP in this range DP. Yeah, so this is uh, subarray DP. So you can read this article and solve the problems which are there, and so you can try this. Uh, did you submit them during the contest or after the contest? Like after 9:30 or before 9:30? Yeah, so in that case, it won't be counted, right? The contest only lasted till 9:30. Like you had to sit for the contest at 8 a.m. and submit the problems. And basically, the time that you took after from 8 a.m. starting from 8 a.m. That would be counted, and you have time to win only 9:30. Like anything you do after 9:30 is not counted towards your ranking. Okay. Anyways, let's write the code for this. The code is very tricky for this, but I'll try to write it correctly. So let's do it together. Okay. Um, so first of all, nums dot size. Then I'll make left answer and right answer. So first of all, left of 0 is um, let's say I am storing the length. Okay, not the index. I am storing the maximum length that we can go from that index. Okay. So if let's call it a, not nums. Okay. So if a of I equals to a of I minus 1, then what we can say is the left of I equals to 1, right? Because I cannot go even till I minus 1. Else, if I is greater than equal to 2 and the sign for like basically a of I minus 1 minus a of I into, let's make it um, okay, let's make we have to do it in long, right? So if a of I minus 1 minus a of I into a of I minus 1 minus a of I minus 2, if this is greater than 0, then this means that the sign is different. So left of I equals to left of I minus 1 plus 1. Okay, right? And else left of I equals to 2. Okay, I think it is correct. All right. So this is how we can find the left array. And to find the right array, actually, we can simply copy paste this, and we can reverse the like basically we can reverse the a vector and actually like just do the left thing for the right one as well. Like wherever there is left written, just replace with the right. Okay. And yeah, right of 0 is equal to 0. Like basically, I'm just doing the same thing. Whatever I did for left, I'm doing for right. And then again, I'll reverse the array A back. And also, I'll reverse my right array. Right. So that's how you can get the left and right arrays. Now, first of all, int answer is equal to 0. I'll first of all check if I do not delete anything. Right. So that is just max element of left or right. Like answer is equal to star max element of left, because this is the length, right? Left of I contains the maximum length if you end at index I. So if I don't delete anything, then the answer is maximum element in this left array, right? Now if I try to delete um, elements, like let's say I is equal to 1, I less than minus 1, I plus plus. So if I try to delete I, can I delete I? So let's say bool flag is true. Now basically the sign for a of I minus 2, like basically my a of I minus 2 minus a of I minus 1 into a of I minus a of I minus 1 should be greater than 0. Okay, this is one condition, and the other condition is for the right hand side, that um, basically a of I plus 2 into a of I plus 1, sorry, minus a of I plus 2 minus a of I plus 1 into a of I minus a of I plus 1 also has to be greater than 0. Okay, so if uh, I is greater than equal to 2, and yeah, if I is greater than equal to 2 and it is not true, like this statement is not true, so this is less than equal to 0, then I will set flag equals to false. Then again, if I is less than n minus 2 and this statement is less than equal to 0, then also I'll set flag equals to false. So this means that I cannot delete the index I. So if flag, then I can delete it, and so my answer can be left of I minus 1 plus right of I plus 1. Okay, and so we will return answer. Now I'm pretty sure that I have messed up somewhere, but let's see. Okay, left of I equal to I? No, actually I am storing the length directly. So left of I would be equal to 1. Okay, it is working for the samples. Yeah, it did not work. Okay, can you explain this multiplication? Okay, so a of I minus a of I minus 1 into a of I minus 1 minus a of I minus 2. Yeah, so basically what I am trying to do is I want to ensure that, um, wait a minute. Yeah, so what I am doing is when I am calculating left of I, Okay, so like let's say I'm an index I. So if this sign right here and if this sign, if they're opposite, then my left of I would be equal to left of I minus 1 plus 1, right? If they're opposite. And to check if opposite, then we can simply take the difference, right? Like this is index I minus 1 and this is index I minus 2. So like um, A of I minus 1 minus A of I minus 2 and A of I minus 1 minus A of I. So like this minus this and also this minus this. So either they have to be both negative, right? If they're both negative, let's say, that means this is the sign and this is the sign. So um, if they're both negative, then the product is positive, right? And if they're both positive, let's say like this, then the product is positive, right? And like if any of them is zero, like if we have equal anywhere, then the answer is not that. Like then this is not the answer, right? So basically, we need that this product should be positive. Okay. No. Even if ai minus 2 is less than ai minus 1 and ai is also less than ai minus 1, then also you get a positive answer. Okay. But yeah, somehow it is getting incorrect. Um, Expected is 3. So let's print the left and right arrows for some. Where should I print this? Okay, let's print it here. Okay. So let's see what is the output for this. So left is coming out to be 1, 2, 1, 2. Yeah, so left is correct. And what about the right? Okay, that I think I just messed up here. Right of 0 should be equal to 1, not 0, right? So let's run this again. It's still not incorrect. Okay. So the right is coming out to be 2, 1, 2, 1. Like I think this 2, 1, 2, 1 is incorrect, right? Why it is coming to be 2, 1, 2, 1? Okay, it is correct actually. This 2, 1, 2, 1 is correct, right? So output is 2. Why is my output 2? Let's understand that. Okay, no, but like I can delete I equal to 1, right? Like when for loop is at I equal to 1. So what am I checking? This is not true. So I won't get into this. And this might be true. So a of I plus 2 minus a of I plus 1. So, okay, actually a of I minus 1 should be there. And here also I plus 1. Because I am deleting a of I, right? I am deleting a of I, so I don't have to check that. I have to check the difference between um, this, like my four numbers which are there, which I have to check. They are um, a of I minus 2, a of I minus 1, a of I plus 1, and a of I plus 2, right? So first I'm checking this thing, and then I'm checking this thing, that they're alternating or not, right? So I think this should work now. Okay. Ah, why this is happening? Okay, not less than equal to 0. I think it should be less than 0. Okay, less than. Hmm. I mean, I passed most of the test cases, but somehow it is stuck here. Um, let's see. Output is 2. Why it is coming out to be 2? So when I is equal to 1, okay, it is not checking any condition. Ah, like if a of I minus 1 is equal to a of I plus 1, then also we cannot delete. So flag equals false. Okay, so now it should work. Yeah. Anyways, so this is how we can solve the last problem. And okay, it is still wrong. Man, why? What am I doing? What am I doing wrong? So expected is 3. Do you guys see any mistake in this code? Just let me know if you do. Um, so you can delete a 2, right? So basically I equals to 2 you can delete. So if I am at I equals to 2, so first of all, okay, actually what I am checking is since these two are equal, if I just change this to less than 0, then let's try. This is just what? How it got TLE, man? It is just O of n, right? Is it because of this? I'm printing this, is that the issue? Yeah, okay. It's correct. So that was the solution, guys, for the last problem. Um, it was not very hard, but it was hard to implement, right? So you can even use DP for this. Like I also use DP to solve this. Then it was easier to code. So you can think of a DP solution as well. But yeah, right now I am explaining only the prefix and suffix logic. But you can look at this code as well, which is the DP code. Like dp1 of I comma 0 means that you have not deleted an element, and dp1 of I comma 1 means that you have deleted the element, so you cannot delete it one so you cannot delete it once more. Okay, so you can think in those lines maybe. But yeah, uh, okay, so this was it for today, I guess. And thanks for watching this. I hope you will I hope you understood every problem, also the last one. And yeah, I'll see you later. Bye bye.